Welcome back to your TxePrep video, and in this video we're going to look at the USACO 2021 US Open Bronze Contest, problem number 3, Acowdemia 3. So basically, the problem, what's happening in the problem and what we need to do is that Farmer John has a 2D grid of cells, and each cell is labeled with C, G, or a dot, where C is a cow, G is grass, and a dot is nothing. And he puts all of his cows on this grid, and he wants them to become friends. So if they want to become friends, they need to meet on a grass-covered square that is either horizontally or vertically adjacent to both of them. And during the process, they eat the grass, so the grass is not usable as a meeting ground for future cows. And the same cow cannot become friends with more than one other. Like the same cow can become friends with other cows, but they cannot like have the same pair of cows becoming friends twice. So he wants to determine the maximum number of friendships between distinct pairs of cows that are being created at the end of this experience. So basically what happens is we're given n and m, which is like the size of the grid, so n rows by m columns, and then there's the actual grid itself. So now given this grid, let's actually try to figure out how we can make the friends. So over here, we see here's our grid and here's our n by m. So what I'm going to do is actually iterate through every single g, so like all of this grass cells, and then I'm going to check if it's possible to even become friends on that cell. And the reason why I'm checking that is because like if it is possible, then I can just mark that grass square off as covered, like completed, and then like no other cow can use a grass square, which is one of the requirements. So I'll start from here. So in this square, I see that there's only one cow adjacent, so there's no meeting spot for two cows to come to here. But now I go to, so that means like this one can't be a meeting ground. So now if I go to this grass over here, well, I see that this cow over here and this cow over here can actually meet together, like they're adjacent to each other, so this becomes a meeting ground for them. But now I go to the next grass square and I see that there's a G over here, so I can see that there's 3 cows surrounding this area. And what I can do is instead of having like two like kind of adjacent cows, like diagonally adjacent cows meet together in the grass square, I'm going to have the opposite cows come together. And the reason I'm going to have the opposite cows to come together is because under no other circumstances can they ever like meet on a grass square except for the one that they're opposite to, right? But in this case, for example, this C and this C can meet over here and they can meet over here, but this C and this C can never meet anywhere else except for here. So since we want to find the maximum number of cows, we can basically just use this kind of a greedy strategy where we always choose the opposite cows. So when I do that, this cow becomes a meeting spot, and that works. And then over here I see that, well, these are the same 2 cows that are adjacent to this, and I see that since they've already become friends, they can't exactly become friends on this grass square anyways. So we only have 2 so far. And then we go to the next grass square over here, and we see, well, there's like 4 cows adjacent to it, and if I want to choose the opposite one, that's like the greedy strategy that we were choosing before, well, I can choose any one of these. So for example, I can choose the top one and the bottom one, or the left and the right one. So I'm, for example, just going to choose the top and the bottom one, and this becomes a potential meeting ground. And then I go to the next grass square over here, and as we mentioned before, like since these 2 cows become friends, like these 2 cows, like this cow over here and this cow over here, can still become friends on this square over here, and this form a friendship because we use the greedily optimal strategy. So now let's actually try going and programming this, and we can see what happens. So here's a program. So the first thing I'd like to do is input everything. So like include all the packages and files, and using namespace standard. And what I would want to do after that is create our main function, so int main, and then the variables that we're going to use outside of it. So the variables we're going to use are int n m, so int n comma m, and then a character array of the grids. So I'm going to just call it grid, and I'm going to give it a, so I'm going to create a constant kind of thing. I'm going to call it const int max, and I'm going to give it a size of the maximum amount that n and m can be, which is 1000, and I'll make it 1005, just to be safe in terms of any out of bounds indexes. So I'm going to give it a size of max by max. So that's basically all the input, that's all the stuff that needs to be input. So now I'm actually going to input that stuff. So over here I'm going to input n and then n, and then I'm going to do a for loop, which is int I is equal to 0, I is less than n, I plus plus, int j, for int j is equal to 0, j is less than m, j plus plus, and I'm going to input the array at that specific I and j, so input grid at ij, and that looks good. And now, since we're done with the input, what we can do next is basically actually start the process itself in terms of figuring out what kind of cows are required. So before I want to do that, I obviously want to create like a counter that basically counts the number of possible cows that we can have. So I'm going to do this, and then what I'm going to do is also create a set. And what this set is going to do is it's going to create a set of vectors. It's a set of vectors of all the pairs that are possible for each grass square. So as we noticed over here, in this grass square, we could get these two cows over here. So the cows that would the potential cows that could be in this grass square would be, for example, in this grass square would be like this cow over here, which is at row 0, column 4. So I'd say 0, 4, and then also this cow over here, which is row 1, column 3. So 1, 3. And we also notice that this is the same thing. It's the same thing that we have for this grass square over here. So we can only choose one of those, and that's what a set does. It stores the unique identifiers. It stores the unique identifiers and makes sure that there's no duplicate. So we can, we can store our pairs in the set only if there's ever exactly two adjacent cows to a grass square. And the reason we won't do it if there's, for example, 3 or 4 is, as we mentioned before, the greedy strategy of choosing the opposite cows, because they can never meet together again except for that in that one case. So I'm going to create a set of vectors and a pair of ints, and the vector will come in a pair of ints. I'm going to call it, for example, just pairs. And what I'm going to do next is basically iterate through every single square in the grid. So I is less than n, I plus plus, and then for int j is equal to 0, j is less than m, j plus plus. And what I'm going to do now is, obviously, I want to iterate through all of the grass squares. So the first thing I want to do is check if the square is actually a grass. So if grid at ij is equal to g, in that case only would I iterate through it. So I want to check if it's a grass square. And then what I want to do after that is basically create the vector of all the pairs that are possible. So for example, this would be a vector of the pairs. And then at the end, if I do end up having two, like exactly two adjacent cows, then I'm going to add those to the vector and then eventually to the pairs set. So I'm going to create a vector, pair, int, basically just to create check all the cows that are adjacent to a grass tile. I'm going to call it v. Or actually, I'll just call it adjacent, just because that makes it more clear. And what I'm going to do now is go in every single direction and check, like basically, for example, if I'm at this grass square, I can check right, left, up, and down. But obviously, if I go up, it would be out of bounds, so I don't want to check that. Basically, just check all of that. And the way I'm going to do that is by using an array. So what I'm going to do is I'm going to call it const int dx, which is a size of 4, and has the values of 1, 0, -1, and 0. And then dy, which is a size of 4, and the values of 0, 1, 0, and -1. And what this means is when I put in a for loop, so my for loop is going to look like this. So for int d is equal to 0, d is less than 4, d plus plus. And I'm going to say that int, I'll just call it like ix, for example. Ix is equal to I plus dx at d. And what that basically means is, for example, I have my I, but then I'm also going to have like I plus 1, the same I minus 1. So, for example, up and down, like up and then down, and then also another 0. But for my dy, I'm going to have like these represent the left and the right characters in terms of the iteration. I'm going to call another one called jy, and I'm going to give that a value of j plus dy at d. So that basically just creates, for every single pair, it basically just creates going left, right, up, and down. But then I want to make sure that those are valid. Like I want to make sure those are valid points. So for example, I don't want it to be out of bounds, and I want it to contain a cow. That's why I'm going to check if it's valid. So I can just create a function for that, and I'm going to call it bool valid. I'm going to give it an I and a j. And basically what I want to check is if it's in bounds. So the way I can check if it's in bounds is by checking if 0 is less than I and I is less than n. And then we want to check j as well. So 0 is less than or equal to j, and j is less than m. And we also want to make sure that the grid at that particular location is actually a cow. So we want to say that grid of I, j is equal to cow. That's basically what we're going to return. So if all these conditions are true, then we're going to return true. And otherwise, if even one of these conditions is false, then we're going to return false. So now that I go down here, I'm going to say if valid, add ix and jy, then I'm gonna add that specific pair to adjacent. So I'm gonna say adjacent.pushback, and I'm gonna give ix and then jy. And just a quick tip, if you're unsure as to what this specific syntax means with like the curly braces, well, basically using curly braces creates a pair. And since vector is like the vector basically has a pair in it, we can just like create a pair of ix and jy instantly instead of having to like write other code to do that. So that's basically adding to our vector. So now we want to check if our vector, if the size of it, so we want to check what the size is. So if the size is greater than 2, and as I mentioned before, that if the size is greater than 2, we can just use a greedy strategy of just choosing the opposite ones, and we don't have to like store anything in terms of figuring out distinctness, because if they're always opposite, we can just add a new like increment like the number of friends. So I'm going to do ans plus plus, but then otherwise, if the size is adjacent.size is exactly equal to 2, then we need to do like the strategy that we talked about before, where we need to add it to the set. So I'm gonna basically sort the set, so like sort the vector that we have over here. So sort begin adjacent and end adjacent, and then I'm gonna add this specific adjacent vector to the pairs. So pairs dot insert, pairs dot insert adjacent. Okay, so you might be wondering as to why we're sorting this array, but like, so the reason we're sorting this array is because the order might be different. So for example, if we look over here, this first grass square had this vector, but this second grass square might have it in a different order, where it's like 1 3 first, so it's like 1 3 first, and then 0 4 second, and we don't want that. And if that was the case, then the set would recognize these two as distinct vectors, but that's not what we want, right? Because we want to make sure that the content are the same. The content are not the same for different vectors. We want to make sure that they're independent vectors. And the way we can achieve that is by sorting it, because if we sort something, we're always going to achieve the same output if their content is the same in terms of what kind of pairs they hold. So that's why we're sorting it. And obviously, as we mentioned before, if the size of the neighboring cows is just, there's only one cow next to the grass square, then we're not going to do anything, because a cow can become friends with itself, sadly. And now that we're done with this, now that we're done with all the logic, we can just output our answer. So I'm going to do cout pairs dot size plus answer, and then I'm going to, that's it. So let's actually run this and see what happens. So I'm going to copy the input over here. So now that we have the input loading in, we can click the answer, we can click enter to get the answer, and we get 4 as exactly what we wanted. And now we can like actually try submitting this and see what happens. So here I am about to submit the file, so let's see what happens. So submit the solution, and it's grading. And after the grading, we do see like we're getting all the, it seems like we're getting all of them right, and the minutes running time, which is good. So now let's go like a quick review in terms of what we covered, what we did for this problem. So the first thing we did was to basically kind of instantiate the variables, and then what we did next was input the variables, and then created a set of vector of pairs, a pair of ints. And the reason we did that was obviously to check whether a certain cow, like whether a pair of cows would not be like a pair of cows will become friends on distinct grasses. So we did that for that. And then we looped through every single grass tile that existed on the grid, and then we basically found all the adjacent cows and checked, well, if the size of the adjacent cows was greater than 2, so if, for example, if we had 3 or 4 adjacent cows, then we knew that we could just increment the answer by 1. But if that was not the case, then we could have just created, like if the size was exactly 2, then we would have sorted the adjacency arrays just to make sure that the arrays were the same, and then input them into the pairs set, and then at the end we would have checked the number of distinct elements in pairs, and then added it to answer to get our final answer in terms of how to solve this problem. So I hope you enjoyed, and I look to seeing you guys forward in the next few videos.